Hello everyone. From this course onwards, from now onwards, we are actually trying to discuss a few things about the unsteady state heat transfer. Okay, so until now we were actually discussing about the steady state heat transfer. Now, what is the difference between the steady state heat transfer and unsteady state heat transfer? So when we talk about unsteady state heat transfer, we are talking about situations where the properties change, or the properties in a case we are considering about, we are talking about temperature changes with respect to time. Okay, so what is that? I'm just going to take an example of the fluid mechanics problem, and then we will see what this unsteady state is. Okay, so if I just consider a small flow, and then let us say I take a small point here, another point here, and the point here. Okay, now at time t equal to 0, so let us say at time t equal to 0, let at this point let this thing be temperature be T1, at this point let the temperature be T2, and this point let the temperature be T3. Okay, it doesn't matter, with at different points let the temperature be different, that is okay. Now let us say at a different time, at a greater time say t equal to T1. Okay, now here we consider the same fluid, and at the same position let this be T11 and let this be T21 and this be T31. Okay, now we say that T1 is not equal to T11, T1 is not equal to T11. Okay, and if you consider the next time interval, that is time t equal to T3, again if the temperature of that particular point is the same point changes, then that kind of a change is called as unsteady state or unsteady state. Okay, that kind of a state is called as unsteady state. So this is applicable in the case of fluid mechanics, or these conditions, all these are applicable in the case of fluid mechanics, heat transfer, and thermodynamics, any other physical problem that we consider which is part of mechanics or mechanical engineering. This unsteady state is the definition for the unsteady state. Okay, so when we come to heat transfer, we actually consider only the temperature. Now let us take an example of heat transfer. And then we'll explain that. So in the case of a heat transfer, let us assume that we have a small stone or something. Okay, so this is a stone or a metal ball or something. Okay, stone, or maybe a metal ball. That will be a very easier way to explain. So let that be a metal ball. Okay, so this is a metal ball. Let us assume that we have already heated this to some temperature Ts. Okay, now the temperature of this metal ball is Ts, which is greater than, let us assume that Ts is greater than T ambient. So the ambient temperature I'm taking it as T infinity. So let us assume that Ts is greater than T ambient. And after that, after some time, after heating it to a temperature of Ts, if we remove the heating source, and let us say the temperature is Ts right now, so what will happen? So from the metal ball, heat is getting transferred to the surroundings because Ts is greater than T infinity, right? So till what time will the heat gets transferred? Till the temperature becomes Ts equal to T infinity. Okay, now what is the process? First of all, what happens is, now initially let us assume that the temperature at this position is also Ts. Then later on, after some time, the temperature at this position becomes maybe Ts1, which is less than Ts. Okay, and after some time, maybe after then the temperature at the center may be Ts itself, and later on this temperature difference just goes on affecting the temperature inside this. Okay, slowly the temperature of the temperature of the border becomes T infinity. But even that time maybe the temperature of the inside part may be greater than T infinity, but then slowly once again the temperature, since the metal ball is cooling down, the temperature may decrease from Ts to T infinity, and finally the temperature becomes T infinity. Okay, so if you take the temperature at the boundary, at this boundary, initially it was Ts, then it becomes Ts1, then it became Ts2, etc, etc, and finally it became T infinity. Okay, so at this particular point, if I am considering this, just this particular point, the temperature has actually reduced like that. Temperature has reduced like that with respect to time. So at T is equal to 0, this is the case. Maybe T equal to T1, this is the case. T equal to T2, that is this is the case. And finally maybe after 10 or 15 minutes, let us assume that it is 15 minutes, so T is equal to T15, then the temperature has become T infinity. This kind of a change is called as the unsteady state changes. Okay, which means that at any particular point the temperature will change with respect to time. Okay, now suppose that the temperature did not change, that is, you are continuously supplying heat from inside or outside such that the temperature at this position, at this particular point, is not changing, then that is called as steady state. Okay, I hope you understood, you got a basic idea of what this steady state is all about. Now until now we were dealing with only what about the unsteady state is all about. Anyway, until now we were dealing with only steady state. Okay, all the equations in heat transfer we were using only steady state conditions. Now when we include unsteady state into that thing, when we include unsteady state also into the equation, then the equation actually becomes a nonlinear second order PDE. Okay, which includes a change with respect to time also. So if we then when we write the equation, we have a term dt over dt. Okay, that will also be, this is the rate of change of the temperature with respect to time. This usually in the case of steady state we consider this to be 0. Okay, this term was 0 for steady state. Okay, steady state. Now when we consider the unsteady state, this actually is not equal to 0. So the unsteady state stays at, so this is unsteady state. At any particular point, this is unsteady state. Okay, now it is not easy to tackle with this problem. That is now the equation has actually spatial changes, where the spatial changes is d square t over dx square, and then you have the time changes also. So when you include the spatial changes and the time changes, and if you include the energy generation terms also, this becomes a very complicated problem. So to solve these kind of problems, we actually bring in some kind of assumptions. Okay, one simple kind of assumption is that we actually neglect the internal changes, that is internal internal temperature gradient is not present. Okay, that is linear, or the temperature gradient is not present. There is no temperature gradient inside that, which means that internal of that body, inside the body, there is no change in temperature. Okay, wherein we actually consider that body as a single lump. Okay, so the body is considered as a single lump. I'll explain all these things step by step. Okay, so the first approach is we consider that as a body as a single lump, and we say that okay, there is no spatial change in temperature inside the lump. Okay, so if we consider that, we assume that at this position it is Ts, and this position also it is Ts, and this position is also Ts. Okay, there are some special conditions where we can actually assume this thing. We'll come to that later on. And then we have at the border of the material, whatever object we are considering, there is a temperature transfer to the surroundings. There is not a temperature, heat transfer to the surroundings, and then where there is a temperature difference, that is Ts is greater than T infinity. Okay, so we consider only the convective heat transfer. We don't consider the heat that is conducted from here to here. Okay, that is what you mean by, so when there is a linear temperature, like if the temperature inside this thing is the same, so we don't have any change in temperature, right? So there won't be, like if the temperature at this position is Ts and the temperature at this position is also Ts and temperature at this position is also Ts, there won't be a heat transfer from here to here and from here to here. We consider this thing to be cooling at the same rate, that such that there is no temperature gradient present inside this. Okay, that is called as the lumped heat transfer approach. Then the second approach is, we consider that the heat transfer is only one dimensional. Okay, steady state. So of course it is steady state, and along with that we consider only one dimensional, which means that we consider only this thing, this term, that is d square t over dx square, or del square t over del x square is considered. Now here we assume that del square t over del y square equal to del square t over del z square. These two will be equal to 0. That is, we have only heat transfer in one single dimension. That is the next way of solving it. When we are solving it in this way, we can actually solve it analytically, and then we can find out some solutions. Okay, we get some solutions, but the case is that we are considering that these two is 0. So that is the second assumption that we are making. Then we have, if you take the three-dimensional analysis, then we won't be able to, it's not easy to solve it numerically directly. In solving the equations directly in analytical method is not almost possible, so it's not always possible. So we actually go for the numerical methods, like the Fourier transform, or maybe the numerical methods like the Newton's Raphson method, or fourth order Runge-Kutta method, or many other methods of that sort. And then we use some softwares like MATLAB, or what can you say, C or C++, or something of that sort, Fortran, anything of that sort. And then we solve all those for all this set of basically the set of the ordinary differential equation that we get from this thing. Okay, so now from here we will actually consider each condition one by one. Okay, so let us actually close this, and then we will see what is the lumped capacitance method. Okay, we'll continue that in the next.